So we learned the definition of linear dependence, and that's when the full rank condition fails. And I gave you two simple examples, and now let me explain what that means. Think about a very simple regression model. In this case, we need at least two independent variables. So I use x1 and x2 and beta 1 and beta 2. In an intuitive interpretation of beta 1 and beta 2 are like this. Beta 1 is the effect of x1 on y so the change in y1 when x1 increases by 1 unit, but at that time, during that change, x2 must be fixed. x2 should be constant, ceteris paribus assumption. So that's the definition of beta 1. So that means then in the data, you should be able to change x1 without changing x2. And then you would if you could do experiments, say, suppose that you are a scientist and you could do a random experiment. And if that's possible, what you want to do here is fix x2, control x2, and see what happens when you change x1 around. And see what happens on y. That's what you want to do. We do not do the experiment, but we would like to observe something similar from the data. So from the data, you should be able to fix x2, but you should see some variation within x1. If that is not possible, you cannot identify beta 1, right? Excuse me. So beta 1, to identify beta 1, you should be able to vary x1 without changing x2. That is not possible, so the problem arises when the regressors are multicollinear. If two variables are perfectly determined by each other, then you cannot change one with the other being fixed. So for example, back in this example, what I want to do here is I would like to fix M but change F. That's not possible. So what you want to do here is I would like to have someone I'd like to compare two individuals. One person is female, so that means M equals to 0, F equals to 1. And I would like to change F to 0 without changing M. For that to be possible, you have to have someone whose value equals to 0. For F equals to 0, M equals to 0. That is not possible. In the data, you don't see those kind of people at all. So it's not, in this case, beta and gamma are not identified. And similar, in this case, you want to change, say you are interested in beta 3, you want to change the education without changing age and experience. Is that possible? But there may be some observations in the data, but that kind of data are really, really rare. And typically, so those who have absurdly, strangely higher education compared to age and experience, or too high or too low education imply they may be errors, data errors, or they may be a very kind of outliers. They may be an extreme outlier. So also there are practical problems. The intuition here is you want to change one without changing the other, which is not possible when those two variables are multicollinear. They are exactly the same thing. Multicollinearity, if independent variables are multicollinear, then you cannot do this kind of variation. Controlled variation is not possible, so the full rank condition fails, so the linear regression breaks down. And mathematically, you can think that an important matrix is not invariable. So those are basically identical. These things are the same thing. Intuitively, mathematically, everything is the same. So this is just an intuition. Let me give you a little, just a special case of that idea, variation idea. So the variation is very important to understand identification, and you are going to use those terms a lot later, maybe when you ask questions in seminars, and when you present your work, people may ask you where is the variation is coming from, or how you identify some parameter. Then this kind of intuition is what you have to explain. Okay, let me do another example, easier example. In this case, I am going to simplify the regression model. Still, there are two variables, but one is constant. So it's simpler example. In this case, multicollinearity problem arises if, so there's basically only one true variable. So intercept is, technically it is a variable, theoretical standpoint, but from the data, no one say constant is a variable. But anyhow, you know what I'm saying. So in this case, the problem arises when variance of the variable equals to 0. It's also, so when there is only one variable with one intercept, then multicollinearity problem just comes down to variance equal to 0 or not. Then the full rank condition is equivalent to that to the condition that variance is non-zero. So then, intuitively speaking, variance equals to 0 means that there is no variation. Simply, x is 1 point, another constant. So, of course, x itself does not vary at all. So beta is not identified. We would like to observe how much y changes when x changes. But if x does not change at all in your data set, then beta cannot be identified, right? So obvious. So as I said, variation is a very important concept in regression, and very commonly used and casually used term. Still delivers a lot of intuition, but is not discussed well and not discussed in many textbooks. So I would like to give you a shout here. You need to understand this. And so then also variation is important because otherwise, if there is no variation, then you are not identifying anything. It's obvious. Well, at the same time, the larger the variance is, the better your result will be. So the variation is also important for the accuracy of your estimator. And to show that, you can think about OLS estimator. I believe you have learned the OLS estimator, and the variance of the OLS estimator is given by this, the simplest possible example. So if you know sigma squared, then basically it's inversely proportional to the sample size and variance of x. So that means the more observations you observe, the better you can do. The more accurate your estimator will be, which is obvious because as you have a larger sample, your estimator will be more accurate. On the other hand, variance plays the same role. The larger the variance in x, so if x changes more, your estimator will be more accurate. It's inversely proportional to your estimator. So it's a very interesting idea. I need to draw a graph. I forgot to make a graph. I am going to draw some graph to explain this, and we'll show you that graph in the next video.